probably go back to the beginning of the presentation. So now we're going to go through some examples and look at the structure of a particular tool set that you can use to build program analyses. And this is what you're going to use for project 1. It's what you're going to use for project 2. It's what you're going to use for project 3. You don't have to use it for your term project, though. The experiences that you get using it for your first few projects should be beneficial, no matter what tool you use for your term project. But if I don't at least give you some background on what LLVM is and how to use it, it's probably going to be lost when you try to actually start working on your term projects. How much? About 20 minutes? Yeah, okay, we can do that. Okay, so what is LLVM? Since none of you have heard of LLVM pretty much, I guess that's not the most relevant question. Most people know about it through another compiler called Clang. How many of you have heard of Clang? Okay, about the same number of people who've heard of LLVM. Clang is essentially an alternative to GCC. How many of you have heard of GCC? Okay, there we go. It's basically an alternative to GCC. It's open source. It was started at University of Illinois, UIUC, and then it got picked up by Apple. Now it's essentially their official compiler. Google uses it extensively. It actually has much better feedback than GCC does. So if something is wrong with your code, you can tell what, which is nice. That's the main reason that I use it. Google actually for a long time has used Clang for all of their development builds, and then they do their release builds with GCC because it has better optimizing right now. Although now actually on Linux, they build their release versions of Chrome with Clang as well. But LLVM isn't just this compiler, Clang. It's actually a set of formats and libraries and tools that can be used for building compilers or doing program analysis of some sort. And Clang is just one client. It is one tool that's been built with LLVM. So what's actually in here? Well, we have a simple typed IR. So we looked at internal representations before, or intermediate representations before. So we have a simple typed IR, and this is bitcode, essentially. It's a consistent representation that LLVM uses for everything. It has a set of program analysis and optimization libraries. So if you want to get dominators, then they have some existing infrastructure in there that will compute dominators for you. So that's great. You don't have to do it yourself. There are a lot of things that are pre-baked in so that you don't have to worry about doing them. You want alias analysis? Great. There's alias analysis built into the system, so you don't have to implement it yourself. You just have to figure out how to use it. Okay. It has machine code generation libraries, which means if you've analyzed something, or maybe you've changed a program by adding in new instructions, you can then compile it very easily. In fact, I have a demo, and we'll go through some of the demo code in these slides. This demo is also available to you online. I'm not sure it's on the course webpage, but it's at least on my teaching webpage. And you can download that and play with it, and it allows you to both analyze code and change it and compile it with new modifications that allow you to do interesting stuff. So you can see some good examples of this. It has tools, essentially, that compose all of these features to perform certain tasks. So it's really, really easy to add or remove or change functionality for any sort of analysis or compilation process that you want because of this nice composable library infrastructure. So how are you going to be using it? Well, you're going to be compiling programs to bitcode. So you can use clang-g for debugging information, you're compiling, and the important thing here is that you're saying emit LLVM. That means you emit the bitcode instead of compiling this to some binary representation. And then output bitcode. You can analyze bitcode. One way of doing this is by using a built-in tool called opt. If you look at the demo that I've given you, I've actually shown you another way to do it as well, where you can build your own standalone tool that will analyze bit code. And you can send around that binary, and you don't have to worry about people using opts and all these command line options. But essentially, opt is something that comes with LLVM that allows you to load in analysis plugins. And you can run those analysis plugins to do whatever you want, really. And you're going to write your own tools. So the example that I have for you is something called call counter. And if you say, okay, I want to count the number of calls to every function in a program, and I want to do it statically, I'll pass in some program. It will return something like, oh, B was called twice, A was called once, printf was called 3 times. So you can start to report on properties of the program.
What kind of language it can analyze?
So it's actually flexible. The question is, what can you compile to bitcode, essentially? Because if you can get it to bitcode, then you can analyze it, right? Clang will compile C or C++. However, there's a plugin, I'm not sure if you're familiar with GCC's plugin infrastructure, but the newer versions of GCC have a plugin infrastructure that you can use an LLVM plugin to generate bitcode if you compile with GCC. So if GCC can compile it, then you can output LLVM bitcode. So that opens up Fortran lots. It opens up lots, right? GCC does a lot. There are also other custom front ends for languages like Java and so forth. It's a little bit trickier though, because static compilation of Java isn't necessarily guaranteed because it's a dynamic language. So depending on what you want to do, sometimes you can statically compile a Java program, sometimes you can't. There are, however, LLVM can actually be used to build just-in-time compilers or virtual machines like the JVM, even for those dynamic languages. It's a little tougher to do your analyses that way though. Okay, so what is this bitcode? Well, if we have some source code for our program over here and we run that magic command we saw before to generate the bitcode, and we can run a second magic command which creates a readable representation of the bitcode, which is nice. It's good to be able to read what you've actually presented. Another way of doing this is by saying clang-e LLVM. You'll end up generating a special language that represents the bitcode, right? So this is gobbledygook, right? But it's not that bad. It's actually understandable. For me, it's downright legible. And for you, it'll become downright legible. I don't know. Maybe it will. Depending on how difficult you find the projects, you might have to have it become downright legible. But I hope they're not too bad. We can see things like functions. So we have a function foo over here. And over here, we can see define void foo. We can see the arguments, I32e. Over here, it was unsigned. This means that I compiled it essentially in a system that says, hey, an unsigned integer is 32 bits, which is good, it should be. Okay, so we've got our function there. We can see that we've got basic blocks. So we have our for loop here with a body that prints hello, and we can see, well, this is really the body of the for loop, and really there's a condition up here as well, but this is the body of the for loop anyway. We can see our call to, well, it says put s instead of printf. That's because, whether or not you realize this, a call to printf for a constant string will get transformed to a call to put s, which just prints a constant string. Okay? But you can see the call to the function there. And you can see, well, we're adding one to our counter variable. We're comparing it against e, just like our condition over here. And then we're potentially jumping back to the top of the for loop.
It looks more like assembly language.
It does look more like assembly language, yes. In fact, that's why you see the way to get this is LLVM disassembly. So this is the LLVM assembly language, essentially. It's a little bit better than assembly language. One, because you've got types. But also, I mean, BR means branch. I like that. Okay, assembly is okay-ish for that too. But if you're going to do a branch, it's going to be a BR. You don't have,
Branch equal to not equal.
right. Now you do have things like compare and equal, but that's relatively easier. It's legible-ish. It's legible to me, and it'll probably be legible-ish to you. Okay. You can notice we also see the edges in here. The label for this basic block is .lr.ph, and we can see that its predecessors are .lr.ph. That shows that it loops to itself, right? It has an incoming edge from itself, and you can see it has a predecessor of 0, which is this one right here. So what is that showing us? Well, it's showing us that the structure of this is something like, here's our entry block, and we can jump to the exit based on this branch, or we can jump to our for loop body, which can jump back to itself or jump to the exit, right? And we can capture all of that information based on these edges here. I think the next slide should show, the branch, which says, well, if we take the true branch here, we'll jump to the exit. And if we take the false branch, we'll jump back to the body of the for loop, right? So the information is all there. It takes a little bit more to parse it. It turns out LLVM also has a system for automatically printing out things like control flow graphs for you. So you can take this, run it through opt or run it through something else that prints out the structure for you, and you get a nice visual representation. Okay, we can see the function call. So it has a lot of libraries that can help you examine the bit code or manipulate it. So if we want to loop through all of the instructions in a program, well, we could loop through every function inside a module. And a module is basically some sort of compilation unit. You got your program, it's made up of functions, right? And so when you compile your program, you get a compilation unit, which is a module. And inside that, you've got a bunch of functions. And every function has a bunch of basic blocks. And every basic block contains a bunch of instructions, right? And so this is how you would loop through that. It's in C++. This is C++11, because anything prior to C++11 is dead to me. C++11 is just much more convenient, much prettier. So you can see here's a way of iterating through all of the functions in a module, all of the basic blocks in a function, and all of the instructions in a basic block. And then we could do something like use the call site helper class to extract information from call or invoke instructions. And I apologize for the tediousness of this, but I'm hoping it'll be helpful. So you can have two different types of call instructions. A call is just a normal call. An invoke is a call that can throw an exception. For most of our purposes, I say, let's ignore things like C++ and exceptions. Just worry about calls. But to extract call site information, we construct a call site from an instruction, and we invoke cs.getInstruction. This is kind of icky, I agree, but essentially what this does is, if getInstruction is non-null, then CS represents an actual call site. It represents a call instruction, right? So at this point down here, we found a function call, right? That's what that means. Because we continued through the loop, if we got a null pointer here, that means CS must represent a valid call site, so I is a valid call. We can also use a casting infrastructure inside LLVM to check the runtime types of things. This is actually a lot more efficient than built-in runtime type information in C++, which tends to be pretty costly. So the infrastructure they have for casting is very efficient, and it allows us to do some more ugly stuff. This is more magic incantation. If you're seeing it on the slides and it looks ugly, that's probably why it's on the slides, so that you know what it is so you can use it in your project. Because I don't want you to search for the ugly stuff. I want you to search for the meaningful stuff that's still painful to find. So what this does is if we say cs.getCalledValue, then maybe we call a function pointer, maybe we called a direct function. We don't really know. Either way, we could have casted that function to be something else. That's kind of hideous, but that happens. So maybe a function took 3 arguments and you want to call it with 2. I can't really praise that kind of programming that would create this, but it happens. So you strip the pointer casts, and this gives you whatever it was that was called. It could be a function pointer, or it could be a direct function. So the next thing we'll do is try to cast it to a function. And if we can cast it to a function, and this is non-null, which is really all this if statement says, then that means we have a direct call to that function. So this gets us whatever was called. This tries to cast it to a function, determine whether or not it was a function pointer, and if it's non-null, then it's an actual function. And so things like getName will allow us to print out the name of the function. Tedious, understandable still?
What if it's a function pointer?
If it's a function pointer, then this will be null.
So it will not parse two programs which calls to a function?
This won't.
Okay.
This won't. If it's a function pointer, then what you might want to do is figure out what it could point to, which I'm not showing you. That might be relevant to your project. Maybe. And there may be some suggestions on how to address that issue on the project page. Okay, maybe. Okay, so you might ask where certain values came from. Okay, maybe we'll continue this on Thursday. You might ask where certain values came from. This is useful for things like tracking dependencies. So you can ask where was a certain value, variable defined, right? Yes. So you can do this because of something called SSA form. And LLVM is in SSA form. What does that mean? Does anybody know what SSA means?
Secure server access.
I guess, sure. That's not the one I'm looking for, but that's why it's kind of nasty here, right? I mean, it's just another acronym. LLVM, IR, SSA, blah, whatever. So what this actually means is that if I look at a program like this, and I want to reason about where this value of I came from, it's tough, right? What is the single, essentially I can ask, what is the single definition of I at this point, at the condition? This could be useful. If I want to figure out how this program behaves, I want to figure out what its dependencies are. And SSA actually stands for static single assignment form. And so it's guaranteed there will only be one definition point for every value. Interesting. It's kind of incompatible with this, right? Any ideas? Okay. So the underlying approach that we're going to take is that we're going to say everything has one definition point, because that makes it easy to say, where did I get my value from? But we can have these special nodes, these phi nodes, and it selects which definition to use at strategic points inside a program. In particular, these will always occur at the start of a basic block, but they only ever matter when you have a merging of multiple control flow paths. Because only when you have merging control flow paths can you have multiple different definitions of a variable that you want to use. Okay? So we can see here that there's a phi node at the start of our loop, which says, well, if you came from basic block 0, the entry point of the function, then I want to have the value 0, right? And if you came from block 1, which is the body of the loop, then I want to have the value defined at 2. So if you came from down here and went back up to the top, you get the value from the previous iteration. And that's what the fee nodes allow you to do. Okay, so you can see exactly the structure and the dependencies that exist inside the program. You know exactly where your values came from, you know exactly why. You can loop over all of the values that an instruction uses, all of its operands. So if you have a particular instruction, you can say, what is the beginning of this operand list? What is the end of this operand list? Iterate through them, nasty C++ style, whatever. Similarly, so yeah, if you have some instruction A equals B plus C, then the operands are B and C, right? You can loop over the instructions that use a particular value as well. So this means you can go either forward or backward in the dependency. Forward or backward in dependencies using use iterators. And the LLVM is strongly typed. This means that every value has a type that you can get by calling getType. And in fact, if you want to print it out, you can call getType and then call dump. And it'll dump out a textual representation of the type. It's going to be very useful for debugging. Types are one way of resolving aliasing. Maybe the easiest way for your project. Okay. We also have an issue since it's explicitly typed. Every type, if you want to use it as a different type, it has to be explicitly cast. So if you have some truncation operation, then you can actually see that truncating, oh, that's not a truncation. Okay, whatever, ignore the name of the function. If you're taking in some 16-bit value and you want to use it as a 64-bit value, you have to explicitly extend it. So all that stuff is still manual, but there is a language reference online and it's still easy to work with. So even though you have to explicitly cast things, you got to do some fidgety stuff, there's a lot of infrastructure in there that makes it easy. Okay. Yes. So it also has types for pointers, arrays, structs, etc. These take a bit more work to deal with, so be it. We'll come back to all of this on Thursday, because that's all we're going to get through. But we'll finish this up. There's not a whole lot more left except for an actual example. Feel free to look at the example before Thursday. Some parts of it get a little complex, but for the most part, the parts that are relevant to your project are actually really simple. Okay, so take a look at your projects, or take a look at the projects, take a look at the papers and decide which things you might want to present. And I guess we'll meet on Thursday.
Aliasing?